Okay. In the last week, we already went through the basic image preprocessing for the fMRI data, of course, using the SPM package. And in this week, we will go to the next step, that is the analysis of brain activation, again, using MATLAB and based on the general linear model. Please go to my website and please download the data in this week, week 7. And we have the handout, and also we have new material files. It includes, I think, one MATLAB mat file and one script file that we can perform the bias correction later. And we definitely will use the same data set that I provided to you in the last week. And I suppose that most of you or all of you have already finished the preprocessing step based on the instruction from the last week. So I think basically you should have all the smooth data with the slice timing, realignment, normalization, correlation, and finally the smoothing process. So you should have the smooth data on hand, then you can proceed to this week. So this is the basic requirement for you to attend this week's class. Okay. Compared to the last week, we have an additional package right here named X-ray View. Actually, this is one of the toolbox also built on the MATLAB platform that can help us view the result that we acquired from the SPM 12. And I think this is also compatible with the SPM 5, 8, and 12. I think most of the version can use this X-ray View package to view the result. It's actually pretty convenient package that we can actually show the 3D brain mapping or the slice view mapping or something. We will show you in the very end of this class. So please do download this package, and I will show you how to again include the paths in the MATLAB environment. So you can use this after you finish the process. And I think I'd like to remind you that some students suffer this kind of the error message or issue when they are using the SPM 12. Actually, it depends on the operating system on your computer. Some of you may suffer this kind of the error message that if your file name or file path include some of the Chinese character or include a space, you may find out that actually during the process of the SPM, it may have some issue about unable to read or to load the image file because of the file name contains the Chinese character or space. So do watch out this point. If you find out that there is a message showing up in the command window of the MATLAB, writing down that cannot find the specific file that you specified for the image preprocessing, then it may be because of this issue. So watch out whether you have this kind of issue. In my system, I think I have the Chinese character and also the space in my file path, but it's worked pretty well. But I know in some old version or some OS system, you may have this kind of issue. So please watch out this point. And I think in this week, we not only finished the preprocessing step, but I think we can go to the very first step about the brain activation. Specifically in SPM package, we call the first level analysis, first level model for the brain activation. It is kind of the model that we can actually using the GLM to identify the brain activation location or brain activation map on a single subject. Okay, so I think we can do this in this week. But before we go for the introduction about the general linear model, I think I have the responsibility to actually discuss the parameter setup of the SPM batch that we used in the last week. First of all, I think I will again put the slide right here. So when we are setting up the parameters of the SPM batch, we may need to again come back and check the parameters that we used for the fMRI. Okay, so I will just leave the slide right here. If you need, just come back to the slide number 6 and check the parameter. So as you may recall that actually we used one of the SPM batch that I set up for you, including so many different steps from the slice timing, realignment, co-registration, normalization, smoothing, and finally come to the segmentation step. And I have already shown you what kind of the files will be created or generated by this kind of a batch. So I won't go through this kind of the detail again this week. However, in this week, I'd like to discuss what kind of parameters we actually set up in this kind of batch file. In the last week, you already learned how to run or how to use this kind of a batch file, specifically the batch underline fMRI preprocessed.mat. This is the batch file that I provided to you in the materials, I think materials 6 in the last week. And you definitely can select the right directory including a specific fMRI data, and you can also specify the fMRI data, I mean after the DICOM import or after the conversion from the DICOM format to the Nifty files. So you can definitely specify these Nifty files in this file import step. And finally, you will also specify one of the anatomical imaging, specifically the 3D T1 weighted imaging for the co-registration step, because we will co-register the anatomical imaging to the fMRI data or the EPI data set, right? So once you specify these 3 input right here, actually you can press the run batch button right here. Then everything will do pretty well. However, we actually need to know how we set up this batch in this week. And please let me remind you again, before you use this batch file, please confirm that the TPM file, actually the tissue probability map of the SPM, please ensure that the file path or the file name for this module normalized estimation and these 2 segmentation steps, please make sure that the TPM file name file path is correct. Okay, if you don't know how to do this, please go back to the last week. I spent some time show you how to reselect or how to correctly specify the file name for these 3 steps. If you forget about this, just go back to the last week and just go to see the online video for the last week. Okay. Okay, so now we start from the very first step, that is the slice timing. What kind of parameter we actually set up in this step? You can, maybe we can go to the SPM. You can do the same thing with me. Again, come to the SPM menu file right here. Please click the batch button. It's right here. And then you can open the batch file that I provided to you in the last week. Of course, you can actually, for your convenience, please set up the current folder right here to the directory that you actually need to use. To me, I actually leave my folder on my desktop right here. Okay, so I can just simply copy the file directory and set this as the current folder. Okay, as I showed you in the last week, that you can actually select the file folder as the current folder in your MATLAB platform. It will definitely help you because it will make you more convenient to select the data file. Okay, so now come back to here and maybe come back to the batch editor right here. Now I try to load the batch file that I actually provided to you in the last week, this one. Just wait a moment. Now you can see the full batch list right here. Okay. And then now we start with the very first step, the slice timing right here. So you can, I will use the PowerPoint slide, but you can definitely click on each module on your SPM and just go through each step with my explanation. So very first one is the slice timing. Now you can see there's definitely an session part right here. You need to specify the file. As we did in the last week, we actually selected the fMRI data. So in our case, actually, we will select 165 files right here. Okay, and then there is a parameter called number of slices. So now you can go back to the slide number 6. Right now you can see that actually we set up 40 slice number for during our fMRI image acquisition right there. So now you need to put in the 40 right here. And the TR repetition time is actually 2000 milliseconds. However, in this TR selection right here, the unit is actually in second. So you only need to key in just number of 2, okay? And TA, you can see right here, TA actually is calculated in this equation. You can actually click the TA on your SPM interface, and you can see there is it's kind of the information panel right here. Now you can see the TA is actually calculated as this kind of the equation, based on this kind of equation. So TR minus TR divided by number of slices. Okay, so what you can do, in our case, I actually key in the 1.95, but actually you can double click on this. You can now actually key in an formula so MATLAB can calculate the result for you. So TR now is actually equals 2 and minus what? 2 divided by number of slices is actually 40 right here. So you can key in an equation right here. And now you press OK, MATLAB will automatically calculate the result for you. So it's actually the value of 1.95 right here. The slice order right here is a little bit complex. You can see actually the slice order, we have 40 slices. However, we didn't actually acquire the slice one by one sequentially. We didn't do that. If you do so, actually the slice number 40 will be very far from the slice number 1. So actually what we did is we used so-called the interleave slice acquisition. That means we actually acquired for example, we acquired all the even slice right here, and then followed by all the odd slice right here. So this is the actual slice order. We start from slice number 2, then 4, 6, and all the even slice to the 40 slide right here. Then we come back to the very first odd number, that is the slice number 1, 3, 5 to the slice 39 right here. You may ask, why start from number 2? Why not start from number 1? It's just kind of the setup for the Siemens machine. If you are using the slice number in the even number, then the slice order will start from the even number. It's kind of the rule for the Siemens MRI machine. But if you set up a slice number with an odd number, for example 39, then actually the slice order will start from the odd number, start from 1. It's kind of the rule for the Siemens machine. If you are not sure about this, you need to ask for the operator. I mean, the one who acquired the image for you. You need to confirm this point. It's a very, very essential setup for the slice timing. If you didn't set these things correct, then your image or the baud signal will definitely be wrong. Okay. And then the final one is the reference slice. You now actually have 40 slices acquired in different time point. How will you do the interpolation? You need so-called a reference point. Which slice would be the reference slice? You need to set up this. In our experience, or in what we do usually, actually we will set up the center slice. In this kind of a sequence right here, we will pick either the 40 or the slice number 1 to be the reference slice. We won't choose the the 2 end for the slice number 2 or slice 39. We won't do so. We will pick the middle slice. So either 40 or 1 would be fine. In our batch file, I select the slice number 1 as the reference slice. Okay. So now when we perform the interpolation to correct the slice timing difference, now we will cause a lesser or small or little error compared to you select the first or the final one as the reference slice. Okay. So this step is actually the setup parameters for the slice timing. And the next step is actually the realignment. As we introduced in the last week, realignment is the step that we try to correct the potential head motion during the fMRI scanning. Okay. However, in this step, actually we used most of the default parameters. We didn't change anything. Okay, we didn't change anything. So what you need to do is actually select the file. However, in this step, actually we didn't really specify the file path right here. What we did, we used a very convenience function, that is the dependency. We don't really need to click the button right here. Specify means that I'm going to specify the specific file within your computer. But we didn't do so because actually they have some relationship between the slice timing and realignment. Actually, we try to use the file or the data set that have already been corrected for the slice timing. Then we will perform the realignment. So what we are going to do right here is we can use this button right here. It's most likely on the right lower corner in the batch editor right here. There's a button called dependency. What you can do is you can click dependency button right here. Then you will see, oh, now you can do is you can select the file before this module. You can see before the realignment, we only have the directory selection and the slice timing. So what you can select is actually this one, slice timing. That means I will use the file that actually corrected by the slice timing step as the input file for this step. So this is so-called dependency. I will depend what output in the previous step to be the input of this step. So what you can do is just double-click this one. So now you can see there is a DEP words right here represent the dependency. That is depends on what is the output from the slice timing step right here. And for all other parameters, actually I use a default, so I won't introduce the parameter for you. And in the next step is the code registration, and you can see we actually want to perform or want to align the structural, that is the T1 weighted images to subjects fMRI or API data. So what we are going to do, you can see when you click the code register estimate module right here, you can see the parameter setup window right here. There are two specific things you need to set up. The very first one is a reference image. So in this case, which one is the reference image? The API data should be the reference image because we want to align T1, we want to rotate or translate the T1 weighted imaging into the API data. So actually the reference imaging is API data. Again, right here you don't really need to specify the API data set. What you need to do, again, use the file dependency. Now you will select, as you can see, I will select the output of the realignment step right here as the input for the reference image. Okay, and the source imaging, definitely you need to manually specify the location of the structural T1 weighted image. That is what we did in the last week. I asked you to specify the location of the MP range, that is the structural imaging file name for this input. Okay, so in this step you actually only need to specify these two things. So one is for the data dependency, and another one is the actual file location for the structural image. And for the other parameters, we will go for the default value that worked pretty well, so we won't change anything. And in this step, actually, you will find out that there is no modified or no new files will be created or generated by the SPM. However, in this step, actually the SPM will estimate. You can see the step is called estimate the correlation step. That means the SPM will optimize, will identify or calculate the optimized transformation matrix for imaging correlation. What is the transformation matrix? That means how we will transform the original coordinates, for example, x, y, these are the original coordinates from the native, that means the original structural T1 weighted image, how will we transform this kind of coordinates into a new coordinate state right here, x1, y1, and z1. This is actually the coordinates that will match the EPI data right here. So actually what the SPM software do in this correlation step is try to optimize or identify the parameters that will help us to transform the original coordinates to the new coordinates right here. So in this step, the SPM will acquire this transformation matrix, and what SPM do is actually, what SPM does is actually to write this kind of a transformation matrix into the header of the anatomical imaging file right here. This is actually stored in the header section of the NIFT file. Okay, so this is what correlation step did in this step. The next one is the spatial normalization. As we introduced in the last week, we actually aimed to co-register subject T1 weighted imaging to the T1 template. That means we try to adjust or normalize the head shape, head fallen to a standard template right here. So you can see this is a subject T1 image right here. It's kind of small and shorter compared to the T1 template right here. But after the spatial normalization, we ask the algorithm to help us to normalize this kind of spatial imaging to this standard template right here. So in this step, what kind of parameter you need to set up? The very first one, again, you need to specify which kind of imaging will be used to estimate the, again, transformation matrix. But this transformation matrix is actually the transformation matrix for spatial normalization, not for imaging correction. Okay? And again, we use the file dependency right here. So we use what's output from the co-registration step right here as the input file for the imaging normalization. Okay. And you can see the following parameters. Actually, you don't need to change too much. But right here, I may remind you again, the tissue probability map, the file path right here, you definitely need to ensure or make sure this file is the right file path in your computer, because we install the SPM from different file paths right here. To me, it's actually the file path for my computer, but not for yours. You definitely need to make sure that the TPM pathway is right. And another one is this one, because we actually acquire data in Taiwan. Taiwan is the eastern country right here. So you should select the regularization term based on the East Asia branch. In default, I think if you acquire some batch file from the American or from the I think the England or something, the default value may be the Western brand. Okay, Western brands. That will be a little bit different. So you should confirm that this is definitely suitable for our data set. And in this step, actually, I mentioned that this is actually the normalization, but the goal is to estimate the transformation matrix. So you can see in the following step, we actually have three right steps for the imaging normalization. So actually, in the previous step, we only acquired the transformation matrix, but in the following three steps, we'd like to use this transformation matrix to really write or to really apply this transformation matrix to, I think, three data sets. The very first one is the anatomical structural imaging right here. We will really apply this transformation matrix to the anatomical imaging right here. And the second one is for the fMRI data set. Of course, we will set the file dependency. So the first one may be the output from the co-registered step right here. That means the anatomical imaging. And the second one, we will set the dependency to this one, realignment right here. Okay, and the final one, we will apply the transformation matrix to the so-called mean fMRI data. Let me show you in the fMRI in the SPM environment right here. What you can do is come to this step, normalize right step right here, and now you can try to specify two things. Under the subject panel right here, the very first one is the deformation field. Deformation field is actually the transformation matrix. Okay, so what you are going to do is, again, I won't specify where is the transformation matrix located. What I did is use the dependency right here. Which step will generate the deformation matrix or deformation field or transformation matrix? It's definitely come from this one. In the normalized estimate step, this step will obtain or get the transformation matrix right here. So what you are going to do is select this one. Okay, select this one as the file dependency. Of course, in my batch file, I already selected everything for you, but you need to really go through all the steps by yourself. And the second one is the images to write. As I mentioned that in the very first one, we will try to apply the transformation matrix to the anatomical image right here. So what you are going to do is actually, again, click the dependency button right here. Now what you are going to select is this one. Because this step will generate the registered anatomical imaging for you. So you will use this one as the input file right here. So this is the imaging that will be applied for the transformation matrix. And for the next step, we will use the same deformation field acquired from the normalized estimate step. But now we will apply this transformation matrix to which one? To this one. The fMRI data that have go through the slice timing and go through the realignment process right here. So as you can see right here, again, I click the dependency. But now what I'm going to do is I will select this one. Okay, this one is actually the image file that I think, or maybe we only need to select this one, realign one. That means we only realign but not reslice. I think this one is pretty good right here. Okay, and the final one, I will again apply the same transformation matrix, but now I will apply this to the main image. That means during the realignment step, not only we will acquire the realigned image, but also we will acquire so-called main image. That means we will average all the imaging from different time point to be a main image right here. So for this step, actually we will acquire 165 realigned imaging for the output. But this step, we will only acquire one data set. That is the mean imaging average across every single time point right here. Okay, so we will have several different imaging that applied for that will be applied for the imaging normalization right here. Okay, 3 steps right here. And in this step, actually, not only the deformation field you need to select and also the imaging to write, you can see that there is 2 writing options are very important right here. One is the bounding box, and another one is a voxel size. I think the voxel size is pretty intuitive, that this one is actually means we can adjust the voxel size for 3 different axes. X, Y, and Z. And the unit again is in millimeter. So you can see after the imaging normalization, the imaging resolution will now become 2 by 2 by 2 millimeter cube. If you may recall that the original fMRI EPI dataset is actually with the voxel size of around 3.4 by 3.4 by 3.5 millimeter cube. But after the image normalization, we will adjust the voxel size in this kind of a setup. But what is a bounding box? I may use this slide to explain what is a bounding box to you. As you may see right here, after the spatial normalization, we actually set up so-called imaging origin in our normalized imaging dataset right here. The origin is actually located in one of the anatomical point we call anterior commissure right here, or in short, we will say AC point right here. And you can see this point. You can see there is the commissure. Commissure means the merge or the combination for some kind of thing. So you can see here is one of the structure, and there is another one. They will meet with each other in this intersect or this specific point. And this one is actually called anterior commissure. Okay, this point will serve as the origin point after the spatial normalization. And now you can see the bounding box is actually a matrix with a size 2 by 3 right here, 2 rows and 3 columns right here. For the first columns, for the first column right here is actually the range of the x-axis. In the imaging data set, actually x-axis represent the left and right direction right here. So you can see this is the AC point right here. If you try to locate the AC point for the coronal field right here, you can see when we say the x range is actually between minus 78 to plus or positive 78 right here. It's actually from the left hand side to the right hand side. So minus 78 compared to the origin point to the 78 right here. Again, the unit is in millimeter right here, not in voxel, but in millimeter right here. So you can see this is from the origin point. This is the minus 78 millimeter right here. This is a positive 78 millimeter right here. Okay, so you can again see the very similar things from the actual view, the same thing. Okay, and for the second column right here, this is actually the y-axis. That means the anterior and posterior direction right here. So you can see the range right here is from the minus 112 to the positive 76 millimeter right here. So you can see this is the origin point. We can now see the range of the anterior and posterior region. You can see the posterior point would with a limit from the minus 112 millimeter to the positive value as the 76 millimeter right here. Okay, again as the using the S point as the origin. And the final one is the z-axis. That means the head and feet direction. So you can see it will start from the minus 70 millimeter to the as high as the 85 millimeter right here. So you can see the bounding box is actually a constraint of the FOV, constraint of the field of view that you can actually use for the subsequent image analysis. So if you set the bounding box too small, what would happen? For example, if you let me use this. If you set up a round factor right here, for example, if I set the minus 70 to the, for example, minus 40 right here, what will happen? Actually, you will only see the image maybe around here, around this bounding box. That means you only have a z-axis as low as the minus 40. So you will lose the information from this section. Of course, this is pretty bad because most of I think a part of the cerebellum may not be covered with this kind of range. So actually, this bounding box is kind of the standard range. If you use the ICBM T1 template as a reference, actually you don't need to change the bounding box. It will just fit for the whole brain region, including the cerebrum and the cerebellum. Okay, so you need to watch out this thing. When will you change this kind of the bounding? When you need to change this kind of the bounding box is actually when you change the template. If you don't use the ICBM T1 template, for example, if you have the children or the pediatric imaging template for your own study, then you may need to, I believe, to reduce the bounding box size for children or pediatric imaging data set. Otherwise, if you use the same adult ICBM data set, you don't really need to adjust the bounding box right here. Okay? And come to this step, the imaging smoothing step right here. Again, we say this is actually perform the spatial smoothing. So what you need to do, the very first thing is again you will select the imaging to be smoothed. And in this case, we actually set up the two outputs right here. So we come to the SPM. Okay, you can come to the smooth. You can see actually you can click on this. You can see I actually select the two things right here. So what are the two specified imaging is actually from this step and this step. We want we won't perform the imaging smoothing on the anatomical imaging. So actually we select the output from the fMRI data and from the mean fMRI data as the input for the spatial smoothing right here. Yeah, that's correct. And the second thing you can see right here is the FWHM. The full name of the FWHM is actually the full width at half maxima. This is actually the parameter for the three-dimensional Gaussian smoothing kernel. As you can imagine that actually if you set up a larger value right here, that means your smooth kernel will growing larger. That means you will actually introduce larger smoothing effect on your image. Normally, the value will be set up between the value, I think, 4 to 8. 8, I think, is the maximum value that you will use. And sometimes if you don't want to really introduce such a huge smoothing effect on your image, you can reduce the value to 6 by 6 by 6. Okay, I think 4, 6, or 8 is the three common values that we normally use. But please do remember that you definitely should use the identical value for three different axes. Do not use 4, 6, 8. Do not do this. Please use three identical values because you definitely want the same amount of the smoothing effect on three different axes right here. So these three different values is the effect on the x-axis, y-axis, and on z-axis. I recommend you to use the identical value for 3 dimensions. Okay, so this is actually the spatial smoothing step right here. And the final two are the tissue segmentation. As we introduced in the last week, you will acquire at least three files that initiated with a letter C right here, C1, C2, and a C3 file right here. They will represent the tissue probability map for gray matter, white matter, and CSF respectively. Okay, so you can see right here. So this is actually acquired by the step of the segmentation right here. So what you need to set up, if you click the segment module right here, the very first thing is definitely the input file. While we have two segments right here, the very first one is actually for the anatomical imaging. We definitely want to acquire the tissue probability map based on the high resolution T1 weighted imaging or high resolution anatomical image right here. So the first segment process, we will select the normalized imaging. This is actually use the very first one as the input right here, because the first one is the normalized spatial normalization for the anatomical image right here. So we will use this one. Okay. So what you should do is you need to be very, very careful when you click this step. And now you have chance to actually select the files right here. This is the input file that will be performed the image segmentation. Now you click the dependency button right here. You will see, wow, these three names is actually the same, right? They have the same name, but you really need to see this clearly that only the first one is what you want, because the first one is the spatial normalization on the anatomical imaging. You definitely will use this one to acquire the C1, C2, and C3 tissue probability maps. So only select this one. Do not select the others because they are EPI data. If you may recall, EPI data has a pretty bad spatial resolution. You won't use them to do the tissue segmentation. You use this one, okay? And now there is another option right here named the self-bias corrected. What is the bias corrected? I will show you in the next slide right there. But just please ensure that you actually select the option that is a self-filled and corrected right here. I will show you what does this mean. Okay, and for the following parameters right here, again you will see they are very important things right here. That is the tissue probability map right here. Please ensure that you select the right things right here. Again, there are 6 different files you need to select one by one, as we did in last week. Okay, this is a very important thing you need to select. Okay, so you can see in this step we actually perform the tissue segmentation based on the anatomical imaging or based on the normalized anatomical imaging. But how about this one? Why use another one right here? Actually, this one, my goal is not to obtain the tissue probability map. What I'm going to do is I try to acquire or try to get so-called bias field map right here. So what I'm going to do in this step is I actually select the third, this one. I actually select the third one, this one as the input file. As you may recall, this one is the normalized anatomical imaging. This one is a normalized full EPI dataset that includes 165 files right there. But this one is the normalized mean EPI data, only one dataset right here. I will use this specific one as the input because I'd like to estimate the bias field map on the mean fMRI data. So what is the bias field map right here? Let's come back to this slide. You can try to actually use the MRI crow to display one of the normalized EPI data right here. Okay, I can do this for you. If you come to the slide that you actually perform the imaging preprocessing, you can see, I think after the image normalization, you will get the file with W, initiated with W. So now you can see we have the file name, for example, this one. W means mean, means normalized, okay? Then you will see there is a mean, there's a file name with MEAN mean. That means this is the mean image file right here. But for the others, you may see this one, WA. You have so many different files. I think there are 165 files right there. So you can see with the prefix W and A, you actually have 165 files right here. This is a full EPI data set. But now what we select is actually this one. Now I can display this one. Oh, sorry. Now this one is this one. This one, yeah. With NII extension right here. So you can see this is the normalized image file. So you can see we have a unified spatial geometry for this kind of image data set. However, if you try to adjust the image contrast on this image data set, what I can do is I will drag a square region by pressing the right button of your mouse, drag it to a certain range, then release the right button of your mouse. Then you can see I can actually adjust the image contrast right here. So you can see actually within the center of the imaging intensity is lower compared to the surrounding area. How this happened is actually the effect caused by the head coil of the fMRI. If you are using the high channel number head coil, for example, we use a 32 channel head coil. This kind of the inhomogeneity of the imaging intensity will become very, very obvious, become very, very significant right here. So you can see this kind of things is caused by the multi-channel, high channel number head coil right here. If you use the head channel like the add channel head coil, this kind of effect won't be this much obvious right here. However, if we use a 32 or a 64 channel, this is a very significant thing that you can observe right here. So you can see this is the acquired imaging. This is the enhanced contrast. You can see the single intensity is definitely pretty low in the middle of the brain. Okay, so we need to correct this kind of the bias field. This kind of bias field. Bias means the difference or the deviation for the imaging homogeneity right here. So we need to correct this kind of a bias field. So what we can do is we can use the segment module that you can see we actually, this one. We actually select safe field and corrected selection right here. That means we will save the BIOS field map from the segment module right here. So we can obtain this is so-called BIOS field map. As you can see, the BIOS field map will tell you that you definitely need to enhance the center of the image intensity. So the imaging homogeneity will be restored. Okay, so what you need to do is you can apply this or simply multiply this the BIOS field map to the original images right here. So you can see on your right hand side, now this is the corrected imaging. Original imaging, you have the lower signal intensity right here, but with the BIOS field correction, now you can see the image intensity become equals compared to the surrounding tissues right here. So if you now again enhance the image contrast right here, now it's pretty good. You didn't see this the dark zone, that the circular dark zone in the middle of the brain. Now you can see it's pretty homogeneous signal intensity right here. You may say, oh, this is a dark region, but this is the putamen region. It originally has a hypo intensity right here. This is the normal things right here. But you won't see this pattern right here. So this is pretty essential. If you use high channel head coil, you definitely need to do the BIOS field correction. Okay. And you may see, actually in this step, the segment module will output the BIOS field map for you. However, it didn't do the BIOS field correction for you. SPM didn't do the BIOS field correction for you. So what you can do is you can actually use one of the manable script that I provide to you in this week. If you unzip the fMRI and analysis 07 underlying materials zip file, and go inside, you may see that there is so-called apply BIOS field underlying cf.lu.m file. This is actually the manable script file right there. What you can do, what you should do is now, after you finish the segmentation step, now you have the BIOS field on hand. What you need to do is you can actually open this M file or this code from the manable. So what you should do is just come to the manable window and click the open button right here. Now select the apply BIOS field underline cf.lu.m file right here. And you can see now it is the code that I drafted for you. But what you should do is once you open this file, there's a run script file button right here. You just click run. Okay, change folder. What this file will do is that this script file will automatically apply or perform the BIOS field correction for all the smoothed or normalized data set based on the BIOS field that you acquired using the segment module. Okay, so once you run this script file, what you need to do is go to the specific data folder. What is a data folder? That means the folder with all the preprocessed fMRI data within this folder, okay? So just select this folder. For example, I can select the one big data folder right here. And now you will see there are type selection right here. You can either apply the BIOS field correction to the normalized and smoothed data set, or simply apply the BIOS field correction to the normalized data set. Okay, you can select either type. In this case, normally we will select the normalized and the smoothed data set right here. Just the first one. You didn't need to change anything. The first one, and press OK. And just wait a couple seconds. You will see a message box right here showing done. BIOS correction for the selected data set is done. So now you can go back to the data folder. Now I go back to the data folder. Now what you can see is not only you will have the files with a prefix W, now you will have a file with the prefix M. So now you can search your file, start with M, and the second one definitely will be the S. So you can see now you will have 165 right here. You have 165 files right here. And this file, compared to this kind of the smooth data set, now we already applied the bias field correction. So what you can do right now is now just drag another image right here. So now you can see if you adjust the contrast becomes very, very beautiful. Okay, it's pretty different right here. Okay, so this is the way we do the bias field correction. So till now we finished all the imaging preprocessing step. I also went through all the parameter setup for you when you're using the SPM batch file right there. So please spend some time digest what I'm just introduced to you. Please do ensure that you fully understand how we set up and how we use this kind of imaging preprocessing batch file. Okay, so now we take 5 minute break right here.